This lesson deals with measuring BJT AC parameters and introducing the Giacoletto AC high-frequency model for a BJT. You can find these notes in the ECE302 ebook in Chapter 10 starting on page 17. In Chapter 5, we developed an AC model for a BJT using this set of curves where we plotted I sub B versus VBE and then I sub C versus VCE for different values of I sub B. And we used these curves to develop a model where we had a resistance between the base and emitter whose value was R pi, and that was the reciprocal of the slope at the operating point. And the collector current is a multiple of the base current by a factor we'll call beta AC. In Chapter 5, we found beta DC as the ratio of IC to IB at the operating point, and that was also equal to beta F. Beta F, beta DC, and beta AC were the same values. This was based on having perfectly flat curves that were equally spaced. Let's take a look at this same idea in a little different way. You can think of AC as the change in DC. In fact, this is how they do it in military electronics. We talk about the voltage across the base and emitter, AC-wise, as the change in two DC operating points. Likewise, I sub B and I sub C and VCE. The value of R pi is the ratio of the voltage across the resistor divided by the current. This would be for AC signals, and that would now be the change in VBE over the change in I sub B. Or again, this change is the change in two DC operating points, typically very close to the operating point that we had here. And that the ratio of this AC collector current to this AC base current would now be the change in collector current over the change in base current, would be equal to now what we call the AC beta. And of course, from our previous chapters, we had that the ratio of IC to IB at the operating point was our beta F or beta DC. But now we'll formally define this as just beta DC. Now, if there's no change in base current, there's no change in collector current. Go back and look up here. So here's the change in base current. So if the base current doesn't change, then the collector current doesn't change, no matter what the collector emitter voltage is. But we saw in our last video on page 16 that there was a change in collector current when the change in collector emitter voltage wasn't zero. In other words, if you had a change in collector emitter voltage, there was a change in collector current. The model we developed in Chapter 5, which is also at the top of this page, doesn't reflect this change in collector current, so it won't model this accurately. If we were to increase this change in collector emitter voltage, we would increase the change in collector current. Likewise, if we decrease this, we would decrease this, for again a value of I sub B that doesn't change. That sounds like Ohm's law. We propose the following by adding a resistor to our current model and see if this creates this effect. I'm going to add a resistor across the current source in the model we had on the previous page, but also the model that we had at the end of Chapter 5 when we created this other variation in the BJT model to compare it to the FET model that we had developed. Now we still would have the value of R pi as the change in IB divided into the change in VBE for both models. But now, if we're going to measure a change in current here, what we want to do is set the current in either element equal to 0. If we have no change in collector emitter voltage here or here, then there'll be no current in here. So the collector current would equal beta AC times I sub B. We could then take that current divided by the base current as a change in collector current over the change in base current, and that would be our AC beta if there was no change in collector emitter voltage. In other words, we would force that to be the same. We're going to do that on the curve itself. Likewise, to find R0, if I could make this 0, I could do that by making this have a change of 0. Make the change in IB 0, then I'll have no current here, and the ratio of this change in voltage to this change in current would just be R0. And I can also measure the value of R0 by looking at the curve and actually taking a rise over a run to calculate the reciprocal of RO. If we take an operating point, we have a value of the collector emitter voltage at the Q point, but we also have the early voltage with a negative of it here as the focal point. I've got a triangle here. If I take the rise and divide it into the run, I get the value of the resistance. The rise here is going to be this point minus this point, which is I sub C at the Q point minus 0 down over here. And then we're going to divide that into the change in voltage, which is the collector emitter at the Q point minus the value of minus VAF. We could calculate R0 off the curve itself, or we could take a small delta change and find it that way too. VAF is a pretty large number, so something on the order of 100 volts or so. We could do an approximation without actually finding the collector emitter voltage by just kind of throwing this away and taking the ratio of these two. Let's take a look at some data and see if we can calculate these parameters off of a VI characteristic. Let's go back to page 16, where I plotted at the bottom of the page the collector emitter voltage versus the collector current for different values of I sub B. I'm going to take a measurement at 5 volts and at 10 volts for different values of base current. Let's go back and look at page 16 again. This is the case of having 200 microamps for base current, 400, 600, 800, and then 1 milliamp. And this is 10 volts, 20 volts, 30 volts, 40 volts. So here's 10 volts. And then half of that is at 5 volts. So I'm taking 10 data points. Let's go back to page 19. And I read these with the cursor, so I read them as accurately as I could. These are the values of collector currents I had for different values of base current at 5 volts, and then doing the same thing again at 10 volts. So beta DC is the ratio of IC to IB at a single point. For the first data point, that was 155.16. For the second data point, the ratio of this to this is 135.88. Ratio of these two, 122.58. These two, 112.82. And these two, 105.27. The value of beta DC wasn't constant, was actually varying for different points on the VI characteristic. Do the same thing at 10 volts. Ratio of this to this is 165.09, and then 144.57, 130.41, 120.11, and 111.99. None of these agree with each other. The value of beta depends on where exactly you're operating. When we're analyzing an amplifier, we might want to find the value of beta DC roughly at the area that we're looking at operating the transistor. Beta AC is the change in collector current for a change in base current with no change in the collector emitter voltage. Here I've got a change in collector current for a change in base current. So I use these two data points to calculate beta AC. In fact, the calculation is just shown here on the bottom. Difference of the collector current over the difference of the base current when the collector emitter voltage is not changing, in other words 5 volts. And that turned out to be 116.6. That's this value here. Then the change in these two was this result, and the change in these two was this result, and the change in these two was this result. And again, none of these agree. In fact, none of the AC betas are the same as the DC betas. And the same is true over here. We want to find the value of our parameters in the neighborhood that we're going to be operating the transistor. We want to get an accurate calculation. I should point out that we used biasing circuits which were independent of beta DC, as long as beta DC was large. Even though beta DC is varying, our operating point won't move around very much. I should also point out that as I sub C decreases, the curves become more equally spaced, and the AC and the DC betas begin to approach each other. The good news is this is all built into SPICE, and it can do the calculations for us. We still have to do the design, but we can verify our designs using the software. The value of R out is the change in VCE for the change in IC when there's no change in I sub B. Let's go back here. So for 200 microamps and 200 microamps, I have a change in voltage of 5 volts, and I have a change in current between the difference of these two. That calculation is shown here, and I get 2.516K, so that's the result right here. Then the next two data points, taking 400 and 400, I get a 1.438K. Then the value of resistance at 600 microamps is 1.64K. At 800 microamps, 857.3, and then at 1 milliamp, 743.3. The slope is changing as we're changing the value of the collector current. We can also calculate this resistance using our formula, using the early voltage. So I did that too. I took a single data point here at 10 volts at a value of the current, but now I use the early voltage. The sum of those two, in this case 10 volts, plus the early voltage from our SPICE model, divided by this current of 33.019 milliamps, and I get 2.272K. Similar to this, but not exactly the same. This is an approximation to the value that's here. We're assuming that all these things go to a single point. They sort of do, but there'll be a slight discrepancy between the two. The big thing to take away from this is that the AC beta does not equal the DC beta at virtually any point, and none of this equals beta F. And the reason is that we've added 2 more diodes to our model in SPICE. So we have 4 diodes, 2 across the base emitter, 2 across the base collector. And those added diodes don't have the beta F term in them, and so they contribute some terms that when we take our ratios, they don't come out the same anymore. For the remainder of the course, we're going to be talking about a DC beta and an AC beta, and we can calculate those by hand by doing this kind of a technique, or we can run SPICE and it'll give us some of the data points that we need. I'd like to present the AC small signal high frequency model for a BJT that was developed by Larry Giacoletto. He took the model that we had for GM-VPi with R0 and Rpi and added a capacitance between the base and the collector and between the base and the emitter due to the diodes that were present there. He also added the series resistances because of the wires and the ohmic contacts. I'll explain why he did this in a little bit. Back in chapter 5 on page 30, we had that GM was beta F over R pi, but now we're looking at the AC results, so that would be the AC beta. And R pi is A to F V sub t over I sub b at the Q point. You bring that up into the numerator. And then the product of these two is roughly the value of the collector current. We could calculate GM based on the collector current divided by A to F V sub t. These are approximations because the AC and DC betas are not the same. Close to each other, but not identical. Of course, we've had that R pi is approximately A to F V sub t over I sub b. R0 we could calculate using the early voltage as the collector emitter voltage at the Q point plus VAF over I sub CQ, or just approximate it with these two terms. The value of R sub X is our R sub B in our SPICE model, R sub C, the uppercase R sub C, and RE, the uppercase R sub E. Of course, from over here, we have that beta AC is GM R pi. So if you know beta AC and you know GM, you can find R pi or any combination of those two. Then we had from our SPICE models, the value of the base emitter capacitance, called C pi, was this expression. And for the base collector capacitance, C mu, was this expression. And then lastly, we could calculate a thing called F of t, which is called the gain bandwidth product of a transistor. This is the frequency where the ratio of IC to IB is equal to 1. You might have an AC beta at low frequencies of 100, but as frequency goes up, eventually the value of beta AC goes down. And this is why he developed this model. Prior to this, they were using the model that had the beta term here, but beta now was some equation in frequency. In other words, a transfer function or Laplace equation. Larry Giacoletto was on the faculty at Michigan State University from the 1960s to his retirement around 1988. And he was very famous. He was one of the inventors of color TV. He had, I believe, about 26 patents. But I did ask him, how did you come up with this? And we were having lunch one day, and he said, well, if you think about the diodes, they have some capacitance, so wouldn't it make sense to put that in a model? But when he did that, he found that this term didn't vary with frequency. This is very nice in that this is an equivalent circuit where all the terms in here are constants. Now again, this is an impedance. It has a term multiplying that varies with frequency, but this takes us back to basic circuit design. And a lot of model development is just that, using common sense to figure things out. This formula for the gain bandwidth product is derived in the supplemental problem sets. I'll have you look at that and see some of the details of how the AC beta varies with frequency. Now for the PNP transistor, we're just going to turn the polarity of everything around. So we'll flip this the other direction. We'll turn this current source in the other direction. And these are AC BJT parameters and the high frequency Giacoletto model.